Let us come to the next problem now. Question C. Water at T1 equal to 100 degrees centigrade and P is equal to 0.4 MPa is supplied Q heat energy is equal to 1500 kilojoule per kg of heat at isobaric conditions in a closed system. Determine the final state of the system. Depending on the final state, find out the change in enthalpy, dryness fraction if required, temperatures etc. at point number 2. So, the state 1 is given at 0.4 MPa pressure and 100 degree centigrade as T1. The pressure is not atmospheric pressure here, therefore, this is not the saturation temperature in this case, point to be noted. So, this is basically again a constant pressure process and Q has been supplied, some heat energy is supplied to this, and therefore, there will be some kind of expansion, alright, and because of which the state 2 will be different from state 1. Let us now again we can understand, we can possibly have a cylinder piston arrangement, have state 1 in that and state 2 can be found out. So, always try to draw some kind of a cylinder piston arrangement or a schematic to show the system first. Try to show your system also on a PT diagram if we are sure about the state, and that will actually clarify a lot of doubts. For understanding purposes, those things are always essential. Okay. So, let us come to question C solution now. So, question C, I can again show a cylinder piston kind of a arrangement here, and again my system could be as shown over here, alright, and this could be my state 1 initially and we can find out the state 2 later. Okay, the first law of thermodynamics tells me that Q is equal to delta E plus W, change in energy and work done from the system. Assuming that, which is a standard assumption, assuming that change in kinetic energy and potential energy and any other energy are 0 and also W others other than the expansion space, other than the expansion work is 0, we can say that Q is equal to delta U plus P delta V, simple assumption, and therefore we can say that state 1 and state 2 we can say U2 minus U1 plus P times V2 minus V1 because the process is at constant pressure, and this is nothing but U2 plus PV2 minus U1 plus P1 V1 PV1, and therefore this will come equal to H2 minus H1 change in enthalpy which is equal to delta H. So, we say that whatever Q goes during this constant pressure process, if all these assumptions are okay, then we say that Q is equal to delta H. Now, we see that the state 1 is at P is equal to 4 bar, pressure is 4 bar and T is equal to 100 degree centigrade, and we also see that Q upon M is equal to delta H. If I just write capital H is equal to small h, specific enthalpy change that we are writing as, and Q is equal to 1500 kilojoule per kg. So, we can say that 1500 kilojoule per kg is equal to H2 minus H1. Now, if I want to locate the state 1, the state 1 is very important that I should know what is the Psat at 100 degree centigrade. We know Psat at 100 degree centigrade is atmospheric pressure. So, I say that 0.10142 MPa or 1.014 bar is the Psat value, which is standard value, and my pressure is 4 bar here. That means Psat T1 is less than P1. What does it mean? If P sat T1 is less than P1, we are in subcooled liquid region. We are in subcooled region or compressed liquid region, alright. Now if I go to table 3, I can get these values, the enthalpy values at 4 bar and 100 degree centigrade. Because I am in subcooled region, I will go to table 3, isn't it? And from here I will get now state 1, the enthalpy related or whatever values I want, I can get it from now table 3. So can I go to table 3 now? Alright, so this is table 3 and let us say 0.4 MPa that we are talking about, approximately 4 bar, and here I can locate the point of 100 degree centigrade at this point, alright. So I can get the values related to enthalpy here, which is my state 1 in this case, alright. So my H1 here can be read from here as 419.39 kilojoule per kg, alright. So my H1 which is what I want because I am interested in delta H. So H1 is equal to 419.39. So my H1 value is equal to 419.39, alright. And as we understand from here, Q is equal to delta H. So my H2 is equal to H1 plus Q by M, isn't it? From here I have got Q is equal to delta H, which is H2 minus H1. I can get the value of H2 from here, and therefore my H2 will be 419.39 plus 1500 kilojoule per kg, which is equal to 1919.39 kilojoule per kg. Now this is my state 2, and now I have to understand, when I know state 2, what I know is enthalpy of state 2. I will have to again locate now where the state 2 lie. Is it also in the subcooled region? Is it inside the dome, or is it in a superheated region? That can be understood now when I again go back to the steam table and locate the value of HF and Hg at 4 bar. Because the process happens at constant pressure, I will go to 4 bar now, which is where I will refer to now other table and get the values of HF and Hg, compare those values with this H2 and locate the state, okay. So let us go to table 2 now and find out those values. So here we can see that for 0.4 MPa we can locate the values of HF and Hg. So HF is 604, you can read from here, kilojoule per kg, and Hg is 2738.1 kilojoule per kg, while our value of H2 is around 1919.39. It means that it lies between HF and Hg. It also means that therefore that this steam is wet steam, or the point 2 lies inside the dome, alright. Had it been more than Hg, it would have been superheated region. Had it been less than HF, it would have been in a subcooled region. But because this is between HF and Hg, the state 2 lies for sure inside the dome, and therefore the state 2 is wet steam. The state 1 was subcooled liquid, and because it has been given some Q value, it has been given some heat energy, it has become now wet steam. It is some vapor plus some liquid, liquid plus vapor together, alright. So let us come back to the solution. So from table 2, we understand that HF is less than H2 is less than Hg at 4 bar, and therefore we say that state 2 is wet steam, alright. The moment I say wet steam, I want to know what is the value of X, and therefore I know other formulation now, that H2 is equal to HF plus X time HFG. I know the value of H2, which is 1919.39, is equal to HF we know that it is equal to 604.65 plus x time 2133.4. From here we can calculate the value of x to be equal to 0.616. So we understood that the value of x is now 616.616. I could also see from the table that the temperature at this value, the Tsat value at this temperature, because the state 2 being the two phase region, the temperature is going to be Tsat value, alright, and that is equal to 143.608. So Tsat value at 4 bar is going to be 143.608 degrees centigrade. This is the temperature, and if I want to plot this process now on a PV diagram, alright, my point 1 was somewhere at this point in a subcooled region, this is state 1, and point 2 has, this is the process that is going to happen at constant pressure, and point 2 will be somewhere at this point because my x happens to be 0.6. At the center, if I say midpoint of this will have 0.5 as a x dryness fraction, this is 0.6. So I can approximately say that this is the process I am talking about from 1 to 2, a constant pressure process, for which I will say at state 2 we have got H2 is equal to 1919.39 kilojoule per kg. I found out that T2 is equal to 143.6 degree centigrade, and I also found out that x is equal to 0.616, and this will be the answer of this question. Alright, so this was our problem. The answer will be the enthalpy at point 2 is 1919, the x2, the dryness fraction at point 2 being a wet steam is 0.616, and the temperature at that point is 143.6 degree centigrade. And this is the answer of this question. From the simple formulation of the first law, depending on the pressure and the temperature given at point 1, and because it has been supplied with Q, the state changes from subcooled liquid to a two phase mixture or liquid plus vapor region. Thank you.